Today, we're diving into one of the most famous failed experiments in scientific history, the Michelson-Morley Experiment. But don't let the word failed fool you, because this experiment paved the way for one of the most groundbreaking theories in all of physics, Einstein's theory of special relativity. Let's set the stage. It's the late 19th century, physics is advancing rapidly, and James Clerk Maxwell has just developed his foundational equations of electromagnetism. These equations showed something strange, that light always travels at a constant speed, that is, 3 × 10⁸ meters per second in a vacuum. But here's the catch. Classical physics and Galilean relativity suggested that the speed of light should depend on the relative motion of the light source and/or the observer. For example, if a star emits light at 3 × 10⁸ meters per second and a spaceship moves towards that star, then the speed of light from the spaceship's reference, according to classical physics, should be higher. But Maxwell's equations didn't agree. They said that the speed of light should remain constant no matter what. To make sense of this, physicists proposed the existence of a medium for light waves, a kind of invisible substance that filled the universe. They called this medium the ether. According to this model, light's constant speed was relative to this ether. Think of it like how sound waves travel through air. Likewise, the ether was supposed to be the medium for light. But there was one big problem. No one had any evidence for this ether. And that's where Albert Michelson and Edward Morley came in. In 1887, Michelson and Morley devised an ingenious experiment to detect the ether. They reasoned that if Earth was moving through this ether, there would be an ether wind, a flow of the ether relative to Earth's motion. To test this, they used a device called an interferometer. This device split a single light beam into 2 perpendicular ones. One beam traveled parallel to Earth's motion and the other perpendicular to it. The parallel one was facing all this ether coming straight back at it, whereas the perpendicular one had no such headwind in its way, leading to the hypothesis that the parallel beam would travel slower than its perpendicular counterpart. The 2 beams would then recombine and produce an interference pattern. It was also expected that rotating the device by 90 degrees would essentially swap the orientation of the 2 beams and thus, due to the ether wind, swap their velocities as well, resulting in a shift in the interference pattern. But when they rotated the apparatus, nothing changed. There was no shift in the interference pattern. This null result was a huge deal. It suggested that the speed of light was the same in all directions, regardless of the Earth's motion through space. Ultimately, this outcome, despite not directly disproving the ether model, failed to provide evidence for the existence of ether. And this was a key finding that later supported Einstein's theory of special relativity. Einstein proposed that light doesn't even need a medium to travel at all. Instead, he said that the speed of light is constant for all observers, regardless of their motion or reference frame. This insight revolutionized physics, giving us a completely new understanding of space and time that some people even had trouble accepting at that time. All in all, while the Michelson-Morley experiment didn't achieve its original goal, its failure is widely considered one of the biggest and most important successes in all of scientific history. It's a perfect reminder that even a null result can have extraordinary significance, not just in your SAC scores, but also in the world of scientific academia. Feel free to head over to the link in the description for a video run-through of a sample question on this new topic, and if you enjoyed learning about this iconic experiment, don't forget to like, share, and subscribe for more such VCE Physics content. Till next time, stay curious, and thanks for watching.